Miss Anjali is our host. She is from Iser, Calcutta. Let us start the
A
proceedings.
very good evening. A very good evening to everyone present here. Thank you for joining this amazing NASNI talk. Night sky and stars have always fascinated humanity. And to unveil such curiosities, NASNI has come up with this talk series, and our today's guest is Dr. Chayan Mondal. I'm very honored to introduce him. He has a strong and successful track record of obtaining, observing time, and collaborating on major national and international astronomical projects. Dr. Mondal has been highly successful in securing observing time on major grounds and space based telescopes, frequently as a principal investigator, demonstrating his leadership in designing and executing research projects. This includes AstroSat UVIT-PI. He has secured numerous PI-led observations using the Ultraviolet Imaging Telescope, the UVIT, focusing on deep field imaging and detailed studies of galaxy populations. Next, deep FUV imaging of HST class galaxy clusters. With UVIT far UV imaging of the Hubble Frontier Field, MACS J0416, and the AEGIS Deep Field. Studies on nearby galaxies, including the Cosmic Fossil, WLM, and IC2574, using multi wavelength observations. Observations of MUSC DIMER galaxy samples and Cepheid 2 galaxies. His other PI proposals includes observations to understand star formation in WLM and exploring the connections between star formations and HI hole in IC 2574. His key collaborations as a co-investigator is that he actively collaborates with researchers globally, serving as a co-investigator on several high-impact proposals, including JWST deep fields. Yes, he is a co-I on proposals targeting major deep fields, including the deep far UV surveys of the JWST North Ecliptic Pole time domain field and the AstroSat UVIT deep field survey of the Hubble Frontier fields. He has also contributed to a large-scale surveys of the UVIT legacy survey of the Virgo cluster and the AstroSat UV deep survey of nearby Abell clusters. SALT spectroscopy. Yes, he is a co-I on the proposal of MOS survey of goods S LYC leakers using the Southern African Large Telescope SALT. Melangic Cloud Study. He was a member of the DAAD grant for the signatures of recent interaction in Mag- Magellanic Cloud through Panchromatic Study, which is REMAP. To include his technical contributions, Dr. Mondal's hands-on involvement extends to the instrumentation itself, having been involved in the in-orbit calibration of the UVIT telescope and is experienced in its data processing. He's also a proposal referee for AstroSat and a member of science team for the Future Space Mission in CIST. Dr. Mondal, we are absolutely glad and honored to have you as our chief guest here and the speaker of our today's session. Without taking much time, I would like you to take up and continue with the session. Everyone is super welcome and thank you for joining NASNI. I am Anjali Mishra, your host.
Thanks a lot, Anjali. So, I mean, you gave elaborate description whatever I have done so far in my career, and thanks for that. So, I can see people joining slowly, and I hope other people will join, so we can just get started. I'll just request if anybody has any questions, we can stop in between. So just unmute and ask me the question if you have. And yeah, I'm happy to stop in between and talk because it should be more interactive. And I'll try to finish in, so it's 45 minutes. And yeah, we can discuss after that. So let me share my screen. Okay. Is it visible?
Yes, yes, sir. Visible.
Okay. So, the title of my talk I kept as a journey through galaxies from local to distant universe. uh, uh, just to mention, like just 1 month back, I joined as an assistant professor in SNBOS National Center for Basic Sciences in Kolkata. So currently I'm in Kolkata, and it's a new place for me. So I'm very, very glad to get this opportunity to talk about my work and take you through the galaxies which I have been working on since the beginning of my physics career. So on the left, whatever you are seeing, if I ask you, you'll definitely give me the answer like what are the sources. So they are galaxies. We see these pretty pictures often in internet. And today I'll basically talk about more about these pretty pictures, what we see and how they are taken and what we can learn from them. Apart from appreciating the pictures, what science we can understand seeing from from these pictures. So when we talk about night sky, so I know NASNI, the members of NASNI, they are very much interested in observing the night sky. So if I go to some place in India where I have some level of light pollution, can you see my cursor also?
Yes, yes.
It, okay, thank you. So some level of light pollution. So you get to see a sky like this. Probably in cities, you cannot even expect this kind of sky. So we mostly see the bright stars in the sky, and with longer exposure, this image was taken with longer exposure, you see these fainter stars. But if you manage to go to a place like La Silla Observatory, which is in Chile, and the Atacama Desert is one of the best place to look at the night sky, and that's why a lot of telescopes are installed there. So this image was taken by Hakon Dahle, and he's himself standing here in the image, and you can see some telescopes. And what else you can see is a patch of bright uh, bright patch on the sky, which is our galaxy, like the Milky Way. And this is taken from the southern hemisphere, and you see like a lot of stars along with the Milky Way rising here. If you see some other part of the sky from the same place, like ESO's Paranal Observatory, you can also see something like this. So uh, there are stars, of course, the bright stars, very faint stars, and there are some cloud kind of thing, if you can see it here. Two clouds, one is larger, one is smaller. Now, when we started observing the sky at very early time, we we knew about the stars, we knew about the planets, but there was a time before 1920 when people were still not clear what these fuzzy cloud-like objects are. So there was a debate among the astronomers about this kind of sources in the sky, and it was termed as the Great Debate in astronomy, which which happened between two great astronomers, Harlow Shapley and Curtis. So they are both American astronomer in the same, almost the similar time, and people are just trying to understand this cloud-like objects for what they are seeing in the sky. And being a great astronomer, Shapley and Curtis, they started putting out two different ideas about these clouds, and it happened like 26th April 1920. uh, uh, they they decide to have a great debate, which is like now we know as the Great Debate, and the debate is to solve the question what are these cloud-like sources are. So with a lot of evidence, Seple presented his case and said, like, we have the galaxy Milky Way, and this cloud-like sources are nothing but some source inside our galaxy itself. So they are part of our galaxy. Now, Curtis was a person who denied this claim, and he said, with some measurements, like these sources, which he called as the nebulae, are actually not part of the Milky Way, but they are separate galaxies like our own Milky Way. So basically, Curtis said these sources are outside our own Milky Way, and they are again galaxies, not anything else. So after the debate, people are still not having the exact proof what are these sources are. So then the person came, Edwin Hubble, with his measurements. So in 1919, he was using this 200-inch mirror of the Hooker telescope, it's a large telescope, uh, to image the Andromeda Nebulae. So we know Andromeda is a constellation, like in this picture you can see this is a constellation, and just near the constellation we have a cloud-like source, which you can see probably here. Now he was imaging some of the stars with this very powerful telescope that time. He was imaging some of the stars in this cloud, like I'll say cloud for the time being. And these stars are actually called Cepheid variables. Now, Cepheid are a particular type of stars who follow a relation between their luminosity and period. So they vary their brightness with time, and that variability has a relation with their luminosity. And people already knew if you find a Cepheid star, you can use this period luminosity relation to find out the distance to the star. And when Hubble calculated using the detected Cepheid stars in this cloud, calculated the distance, he found these stars inside the cloud is located 10 times further away than the age of our galaxy, which we already knew. And this kind of surprised many astronomers like Shapley, who was claiming like there was nothing outside Milky Way. Everything we know, everything we see in the sky is part of the Milky Way. So after Hubble's discovery, people were convinced like this nebulae, the cloud-like source we see in the sky, they are actually a different galaxy outside our Milky Way. And like M31, the Andromeda, which you see here, there are hundreds and thousands of nebulae in the sky, which immediately after this discovery, Hubble started characterizing. And after this report, when it was presented to Shapley, he gave a nice comment. Like he said to the community, uh, like he said, the letter from Hubble, what he received, this letter actually destroyed his own universe, which he was uh, thinking the Milky Way is the entire universe. Now, with the discovery, the beginning of extragalactic astrophysics happened. Like we came to know about galaxies existing outside our own galaxies. And this has happened in 1923 after Hubble's discovery. Now, today's talk will be mostly about these galaxies which are outside our own Milky Way. We are living in a galaxy which is, again, there are a lot of things to know about our own galaxy, but I thought of talking about mostly galaxies which are outside our own galaxy. So we'll try to learn few things about these galaxies. What is a galaxy? How do they form? What kind of galaxies we see in the sky, their classification. Then a little bit knowing about the local galaxies, which means the galaxies which are nearer to us. And finally ending with galaxies which are very, very distant from us. Now, I'm starting with a basic idea of how star forms, because to know a galaxy, we have to know, sorry, to know a galaxy, we have to know stars, because stars only is the main building block of galaxies. So if you see this picture, like we know stars from a molecular cloud. This is a molecular cloud, and because of the gravity at some density, this molecular cloud start induce a gravitational collapse. And when it start collapsing, it increases the density and temperature in the inner part. And at some point, it form a protostar like this with a disk around it. And with time, this disk evolves, the protostars also grows and increase its temperature and reach a pre-main sequence phase. And finally, we have a star with some planets orbiting around it. So this is how a star form. To give a better picture here, like when you have a large cloud like this, you actually can form a lot of stars at the same time. Like this is a simulation, and we see from the beginning to 3.4 mega year, the cloud has formed so many stars here. And if you allow the cloud to evolve even further, you start forming more and more stars. So this is how a group of stars form from a giant molecular cloud. Now, the formation of galaxy follows a similar rule, but now we are looking at a very large scale. So this is distribution of gas at very, very early universe. Now, the bright knots, whatever you are seeing here, these are the region where the galaxies start forming first. And how they form. So similar to a star, a galaxy formation starts with a huge molecular cloud, like a huge reservoir of cold gas. And as soon as the cold gas start collapsing, as I showed in the last slide, so it start forming a lot of stars inside that cloud. Now, we define a galaxy when we have two criteria satisfied, like the stars from at a large number, and also it has a dark matter potential, which actually induce the collapse uh, in a large scale. So instead of forming a single star, this kind of extremely large reservoir can form plenty of stars. And these stars, after the formation, they are bound to a same potential. And then uh, we actually end up having a galaxy like this. Now, if this same cloud has some initial angular momentum, like some rotation, then definitely to conserve the angular momentum, the once it is collapsing, it also starts flattening. So you end up having a disk-like structure like this. So depending on the angular momentum, the collapsing cloud will form either a disk-type structure or a spheroid or ellipsoid-like structure like this. So now we know uh, how the galaxy actually forms from the primordial gas under the dark matter potential. So once we know how galaxy forms, let's look at some of the images of galaxies we normally see in internet, like a lot of galaxies with pretty pictures. So this is one such galaxy, and I have just shown here three different images of the same galaxy. So uh, this image is taken using ultraviolet telescope. This is using optical telescope. This is using mid-infrared telescope. Now on the bottom, if you see spectral energy distribution of the galaxy, so which means when we see a galaxy, we basically count photons emitted by the galaxy in different telescope, right? Whatever telescope we are using. Now, this entire spectrum basically says the amount of flux emitted by this galaxy at different wavelength. Now, this is the UV part of the wavelength, and this is the optical path, and this is the infrared path. So at different region, we built different telescopes to see the same source. And once we observe the same source, we see pictures which are slightly different in characteristics. So this is how we know, oh, okay, so there is a galaxy, it is emitting this many photons in ultraviolet, this many photons in optical, and this many in infrared. And if we combine the whole picture, we get to know more about the galaxy. So that's how we can actually define a galaxy as a gravitationally bound system of both dark matter and baryonic matter. But the baryonic matter, as I showed here, is made up of stars, and they can have different age and metallicity. Like these two picture on the left and middle, these are emission from the stars. It will also have this interstellar dust, which are complex molecules formed out of carbon and silicon. And the picture on the right basically shows emission from this interstellar dust. And of course, we also have this gas, which was initially there and formed the galaxy. And the gas can exist in three different forms, like atomic gas, molecular gas, and the gas in the ionized form. So now when you see a galaxy picture, you should ask yourself, like, okay, I'm seeing the picture of the galaxy, but what it is actually? Is this the emission from star, emission from dust, or emission from gas? As soon as you know the wavelength of that image, whenever you see in the internet, if it is UV or optical or near infrared, it is mostly from the stars. If it is in the mid infrared or far infrared, it is the dust. And if you see something like this radio 21 centimeter or sub-millimeter emission, it is from the molecular gas. So now we know how to understand say, like when we see any image of the galaxy, what it is actually. Now, as I was saying, like Hubble first discovered the case like there are galaxies outside our own galaxy. Immediately after this discovery, he also classified these sources into primary categories. Like if you see this Hubble tuning fork diagram, we call it Hubble's tuning fork diagram. On the left, you see structures which are more like rounder and smooth. When you come to the right, there are two uh, bifurcation. On the top, you see uh, smooth disk with some spiral structures here. On the bottom, you see central elongated structures, which we call as bar structure, and then have the spiral arms. So this was a classification scheme introduced by Hubble in 1920s, and we still kind of categorize galaxies in terms of this name. So when you see galaxy like this, we normally call it ellipticals. And when we see the spiral arms, we call them spiral galaxies. Apart from this spiral structure, there are many other structural characteristic of galaxies which we know today, but I'll not talk about those complex structures. Uh, so if you see the reservoir of observed galaxies today, we actually have plenty of different structures apart from this introduced by Hubble. So on the right, you are seeing different galaxies, and these are actually real galaxies, not like hand-drawn or simulated. Every point in the picture is a galaxy, and you see what so many peculiar shapes uh, the galaxy exists. And this is a project, a community project named Galaxy Zoo, and anybody actually can Google it, just explore the website, and being a user, you can also participate in their community projects. Like they also have different projects like where they ask people to click on the galaxy and characterize the class of the galaxy, whether you see some spiral or you feel the galaxies uh, having more rounder or more elongated shape. So I can see another beautiful thing on this slide here. So if you read this, we can see there is a word called science written here, right? And all these letters are actually formed using the real observed galaxies. Just to appreciate the fact, like when we observe the night sky using great telescopes, we actually see galaxies of so different structures, and we are still trying to understand the formation, how these kind of structures evolve, so different structures exist in the universe. Going ahead, as I told, three different classification we actually know. The elliptical galaxy, which are more smooth and structureless. So this kind of image, if you see, it is mostly elliptical galaxy. And elliptical galaxy, the main characteristics is like this galaxy doesn't have much gas left to form new stars. So it's kind of a very old diet uh, uh, galaxy, you can say, where the star formation is not happening or will happen in the near future. Whereas we have galaxies like this, spectacular spiral arms, lot of star formation ongoing along the spiral arms, and they are known as the disk spiral galaxy. Mostly the star formation we see along the spiral arms, where you can clearly see the red knots along the arms. These are, so the red knots are basically sites of Young's massive stars. And apart from these two class, the abundant number we have actually in the sky, which are irregular galaxies. So if I say like they actually, in terms of number, they dominate, and sometimes they even go up to 85%. Uh, if I see in the nearby near to the Milky Way. So these galaxies are relatively less massive. They have irregular structure, less uh, metal content, and also uh, a patchy star forming regions. Like they can have star formation happening very outside, uh, very irregular distribution of star formation, not like the spirals we see on the middle. So yeah, to summarize here, like we now know how galaxy form, how many different kind of galaxy exists. And if I see now image of a galaxy, now I know how to identify what I'm seeing, like the emission from stars or gas or interstellar dust, or what kind of galaxy it is, right? Okay. Now I'll just go back again to understand the emission from the galaxy a bit more a different way. So we know stars, emission from stars are kind of the black body radiation. So here you can see three different black bodies, and the peak temperature of these three different black bodies are different. So this is the hottest temperature we have, which is in the ultraviolet, peaking at the ultraviolet is the visible range, and this is in coolest temperature and the infrared range. So if I say there are three different stars, which is represented by these three black bodies, so this will be the most massive young star, this is intermediate, and this is a like less massive cool star. As I said, stars are the main building blocks of galaxies. When we see light from galaxy like this image or this image, this light is actually contributed by a lot of stars, right? Particularly when I'm seeing in UV and optical or near infrared. So if I break it down like this galaxy emission as a function of wavelength in terms of a summation of stars emission. So if a galaxy is emitting very uh, like a lot of photons in the ultraviolet range, where you can see here, this is the ultraviolet wavelength range. So this will clearly say to get a lot of emission in this range, we have to have black bodies like this in the galaxy, which says we have to have massive young stars in the galaxy. Now, if you see a galaxy which is emitting less number of photons, the shape of the spectrum is like falling on the ultraviolet side. So this is basically uh, representing a galaxy which is not forming a lot of stars in the recent time like the other one. So it probably has not formed massive young stars in the recent time. That's why we see very less number of photons in the ultraviolet range where emission from the massive stars comes. Now, when you see any spectrum of galaxy, you can actually just by seeing the shape of the spectrum, you can try to say without seeing the picture what kind of galaxy it is. So this is the beauty, uh, how astronomers can just use the measurement, construct this spectral energy distribution, and try to characterize what type of galaxy we are actually observing. Now, uh, some astronomers took measurements from millions of galaxies, like they took more than uh, more than a few thousand, 100,000 galaxies and plotted a diagram which is shown here. So on the x-axis, this is the stellar mass of the galaxies, so how massive they are. And on the y-axis, it is a color U minus R, which represents their star forming nature. Now we have two clouds forming over here. So this is less massive, more bluer, which are actually this kind of galaxies with steeper slope, and a lot of galaxies forming a cloud here, which are like this type of galaxies with more redder color, shallower slope. And in the picture also, it is quite clear. So if you go from this angle, this corner to this corner, you see more blue young galaxies to more redder older galaxies. So basically we move from here to here, and in the picture we move from here to here. Now from this y-axis parameter, we also can understand what is the star forming phase of that galaxy, whether the galaxy is forming stars or it has actually finished forming most of the stars and kind of in the quenched phase. Now, what drives the evolution of a galaxy? We kind of saw this so many different kind of galaxy exist. So how they evolve differently. It can be decided by their mass, their star formation rate, how much metal they have, and what environment they are actually located. So like we came to know about this three different kind, and in terms of mass, the massive will be the spiral and ellipticals, and when we talk about less massive galaxies, they are mostly dwarfs. So they are called dwarf galaxies, which are very, very less massive. In terms of star formation rate, we see galaxies which are extremely star forming, like starburst galaxies. There are galaxies which stopped star formation, like quenched galaxies. For the metallicity, we have galaxies which has very, very high metallicity, like more than the solar metallicity. We also have galaxies which are extremely metal poor. So metal poor means we still have the pristine primordial environment in the galaxy somehow. And these are also interesting candidate to understand the earlier uh, phase of the universe where the galaxy formation just started. And for the environment, we have galaxies which are like interacting with each other. So galaxies which are in the cluster in a small group. There are also galaxies which are isolated, not interacting, not inside any group. So now to understand the ongoing star formation rate, it is important to know the mass, star formation rate, their metallicity, which environment they are. All these properties will say why we see a star formation, recent star formation happening, or why we don't see a star formation. Again, like just to give a better idea, a galaxy which is located in a group like this, because of the interaction, it can induce more star formation, and this increased star formation rate can enhance light, bluer light specifically, and the galaxy will move in this diagram over on the lower side in this y-axis. So and this is how the stars are distributed. We know like the massive stars are over here, which are hot and luminous. So it connects like how the star evolves and how the galaxy evolves, and combining the light from different stars, we get to know what kind of integrated light we expect from galaxies. Now let us try to understand some galaxies we have near to us. So this is a picture where in the center, let's say our Milky Way is there. And there are a lot of names here you can see. One is Andromeda Galaxy, so which is the nearest, most massive galaxy we have. And combining all these galaxies within the 2 megaparsec diameter, like from end to end, we form a group which we call as local group. So our Milky Way, like our own galaxy, is part of a group which we call is the local group. And so every year there is some new galaxy actually discovered in this group with the advancement of observation, like new telescope, more sensitive telescope observations. We discover very, very faint nearby galaxy, and which actually the Milky Way satellites. And this number increases. So currently we have more than 50. Uh, when we go outside this local group, little outside this local group, we can see this distribution of galaxies within 11 megaparsec. So here the local group was 2 megaparsec from end to end. Now we are defining another group of galaxies which is called local volume, which are distributed 11 megaparsec from the Milky Way, like this. This is the distribution in the sky. And this number also increases every year. And I just showed a distribution from an old picture, like we have this many galaxies very near to us, like around 1200 galaxies. So most of the pretty pictures you see in the internet for individual galaxies are among these 1200 galaxies. To get familiar with our own local group, like where the Milky Way is located. So if you see, like this is the two bimodal distribution, one around the Milky Way, lot of faint low mass galaxies, and there is the Andromeda galaxy over here, and again lot of satellites of Andromeda and low mass galaxies. So two massive galaxies, this is the Andromeda galaxy and our Milky Way, forming a group with their own satellites. And if you see the distance to the Andromeda galaxy is 770 kiloparsec, around that. And you must have heard like Andromeda galaxy is actually approaching Milky Way, and someday the two massive galaxies can actually collide with each other. So yes, like we know Andromeda has a blue shifted spectrum, which means it is coming towards us. So which means this barycenter, with respect to this barycenter, these two bodies are actually moving closer. And with this 120 kilometer per second, the speed estimated, you can actually calculate how many, after how many years, because you know the distance, you know the speed, so you can calculate how many years it will take to Andromeda to come and collide with the Milky Way. So both are approaching towards each other. So maybe you can try tonight after this talk. Apart from the massive galaxies, we have also like this less massive dwarf galaxy, like this large Magellanic Cloud and small Magellanic Cloud, which we see in the sky like this. And this galaxy was discovered just last year. And you will surprised to know this is a galaxy formed with a few hundred stars, and it has even a total mass estimated for the all the stars it has is even less than around 100 solar mass. So from Andromeda, where you have Milky Way, Andromeda 10 to the power 10 to the power 11 solar mass mass, where you have only 100, a few hundred solar mass galaxy. So just to appreciate, like galaxies exist in so many different form, and even if we look at our own nearby universe, we get to see new galaxies every year. So imagine what it happens when you go very, very far away. How many this type of galaxies are actually there, which we cannot see with our today's facility. Okay, so fine. Now let's look at the deep universe where we go to the distant galaxies. Like I was mainly talking about this region. Now, a region of dark patch of the sky where there are no bright stars. We can use our observing time to image or observe that part of the sky for a long time. Like, for example, this region, we don't have many bright stars. So this is a very low exposure image where we only see the stars here. Now, it's kind of taking pictures of nothing in the sky. When you take pictures of nothing for a long time, you can see something like this. So this is the same region over here, an image taken using Hubble Space Telescope for 11.3 days of exposure time. So you can imagine how much time a telescope has exposed to take something like this incredible, which has changed our entire idea of the universe. So every point in this image is a single galaxy. And these galaxies are not at a particular distance. They can be very near to us. They can be very far away from us. So using this kind of observation, we study galaxy evolution from different cosmic time. Now we do this using different telescopes like Hubble Space Telescope, which is optical and near infrared. Recently, you have heard about the James Webb Space Telescope, which mostly observes in near infrared to mid infrared band. And using these different telescopes, we can actually probe different range in the cosmic time, like the redshift. We also have our own ultraviolet imaging telescope, which I have been working a lot, India's own UV space telescope. And this also can probe galaxies at particular redshift like 0.5 to 1, which you can see here. Okay, so now since 2021, when the James Webb Space Telescope was launched, we have been seeing this kind of images in the internet. And as I said again, like these when you see it for long time, different distant and different properties. So thousands of galaxies you can see in the picture here, and again the same galaxy cluster imaged using Hubble Space Telescope. You can see the image here. Now, astronomers are using this kind of observation to understand galaxies at very high redshift, where the universe we can probe the universe at its very earlier phase. And these are some of the names you may see in the internet where similar kind of observation are being taken. Now, when we see this picture, how to know like which galaxy is located where? Like if I say, ask you like whether this galaxy is farther away or this galaxy is farther away, which is near to us. Now, the way we measure the distance to a galaxy is using the spectral lines. So when we take a spectra, we see this kind of emissions. And once we identify the lines, we try to find solution where from the observed frame, we can actually, this is the observed frame, and we can go to the rest frame where actually the photons are emitted. Now, when this solution matches, we actually get to know about the distance of the galaxy, how far it is. So this is the spectroscopic way of determining distance from distant galaxy. There is another way called Lyman break technique where uh, we use, instead of spectra, we use different bands like this. So every telescope has these photometric bands, and we can observe a same galaxy in different photometric bands like this. Now, when you start from the radar side, like this is the infrared side, and this goes to the optical and then the bluer side. At some point, if you this filter, that means the spectrum, which is shown in the gray, has so in this filter, the Lyman break, where we see the certain drop of the emission of the galaxy actually has reached. And once we know the position of the Lyman break, these two different techniques to understand where the galaxy is located, how far. And since the Hubble started exploring, the records of most distant galaxy has been broken many times. So this galaxy, if I frame it in the cosmic time, so here if you see redshift 11.1, this is our present modern day galaxy, and we are traveling here, here, and here to the reionization era. And this galaxy was standing as the most distant galaxy when the Hubble was operating, 11.1. So it's named as ZNZ11. This is the galaxy image. But once the James Webb started operating in 2021, 25th December, it was launched. So we are seeing even galaxies which are even farther away from this GNZ11. So since last year, this was the most distant galaxies at redshift of 14.3, 4 something, and this is the name. Very recently, we have so today, as of today, this is the most distant galaxy we know. With the coming time, again, this will again be changed, and this galaxy is at 14.42, I think. Yeah, 14.42, as named as MOM Z14. And as I showed, like, so the break of the spectrum helps us to confirm how far they are. So you saw all these pretty pictures, but this picture, which is not looking pretty, but this is the most distant galaxy we know today. So the light from the most distant object. And yeah, there are many similar galaxies which are discovered by the James Webb Space Telescope. Like when you see local galaxies, they have nice structure, uh, uh, irregular spirals, and this smooth ellipsoid. But if you look at the distant galaxies, they don't have this well-defined structures which we see here. So mostly they are patchy, clumpy, and smaller in structures, right? So some of the galaxies which are far, far away from us, if you see here. Now, there is a recent paper which titled like Galaxies Going Bananas. Uh, uh, so they reported from a nearby universe. If you go to a distant universe, this type of structures increases like 2 times or more than that, 3 times. So they are trying to understand, like, at higher redshift, why this kind of elongated shapes exist for most of the galaxies. This is one interesting result which came up after the James Webb started observing. Uh, Again, there are some reports of not only the banana kind of structures, but there are reports like the disk structures, like you see on the right here. These are disky structure where in the nearby universe, if you will see, you'll see something like this. But as they are far, far away, we don't see pretty well-resolved structures, but they are disky structure. And this paper reported a large fraction of disk structure at higher redshift, which again puzzled a lot of people. Like the paper title "Panic at the Disks." So why, uh, how this high fraction of disky structure can exist at very high redshift, where we mostly expect to see clumpy structures. So this is uh, another new results coming up very recently at the higher redshift size. Now, to compare how galaxy evolve in terms of their size and mass with time, so from the top to the bottom, if you go, you are actually going from very nearby universe to the very high redshift universe, like the distance universe. And on the x-axis, we have the mass of the galaxy. So you see the tail of this side is the massive end is going this way, right? As you go farther away from us. So as we go to the distant universe, the number of massive galaxies reduces. So we don't have very, very massive galaxies forming at the very early time of the universe. Whatever massive galaxy we see, they are actually near to us, relatively near to us. Also, their number changes, you see on the y-axis. Another thing is the size of the galaxy. So we know as we go from near to the far away, distant from us, the galaxy size decreases. On the y-axis, we measure the size of the galaxy using a lot of samples, and we see the reduction in the galaxy size. So now I quickly just go a few highlights from the ultraviolet imaging telescope, which is part of India's own AstroSat satellite. Uh, as I was talking about Hubble Space Telescope and James Webb, they mostly see galaxy in optical and infrared, but ultraviolet imaging telescope observe this part of the galaxy spectra, which is the UV range, and we can actually do interesting science using photons which are coming from the UV or even from the ionizing part, like which is extreme UV range of the galaxy. As I don't have much time, I'll be a bit quick here. So we can do a lot of science using this telescope, ultraviolet imaging telescope. So here is the region of the ultraviolet emission, and we are trying to probe this part of the spectrum of the galaxy using this observation. So AstroSat was launched in 2015, and uh, this uh, this year actually is completes the 10 years, and ISRO is organizing a conference early next year to celebrate the 10th year of AstroSat in the sky. And apart from the X-ray telescope, we have one ultraviolet imaging telescope here, which is equipped with two telescopes, like one observes in the far UV and another in the near UV and optical. It has multiple photometric bands like it, and we can reach a very superior angular resolution than the earlier space UV telescope, which was launched by NASA. If you see the same source, which was not quite well resolved here, the India's ultraviolet imaging telescope could resolve these two sources and has given us a lot of benefits to understand distant galaxies, nearby galaxies in much better way. So I've been working with nearby galaxies from this ultraviolet imaging telescope, and you see irregular. I was talking about irregular galaxy. So each single dots are UV emission from these galaxies here. So these are very high energy photons coming from these galaxies. This is a spiral galaxy, flocculent spiral galaxy, a spectacular image taken by UVIT. And we studied their properties, the star formation rate, how big they are, how hierarchically distributed they are, and kind of given a fast idea of young star forming regions resolved using this instrument, and tried exploring why these different galaxies can form stars at so high rate in the recent time. As I was also showing some images of the distant universe. So if you remember the James Webb images, so this is a similar image taken by our own UVIT, and every tiny dots you see here are galaxies, and these photons are not like the Hubble sees or the James Webb sees. These are all high energy photons because we are using the UV telescope. Whatever photons we detect, they are high energy photons, either in UV or in the extreme UV range. And you can see how well we can resolve this galaxy. So though we cannot see a spectacular structure or shape of the galaxies, but every photon we count using this telescope is actually very important to do a lot of science. And yeah, as I also said, like Hubble and James Webb might have a better resolution, but every telescope is designed for its own purpose, and AstroSat UVIT was designed for its own unique capability of seeing or capturing uh, UV photons from galaxies. So you can see, so this galaxy which we see on the right is also picked up by our own observation. So yeah, just to finish my talk, the most interesting discovery I'll say has come, which was contributed by UVIT, I would say, is the discovery of ionizing photon from galaxies. So these photons, if you see, they cannot be easily observed from a galaxy, because when a photon has a wavelength of less than 912 angstrom, it actually can be absorbed when it interacts with the hydrogen atom, because hydrogen atom gets ionized by this photon, and once the hydrogen atom get ionized, you lose the photon. So a galaxy which is emitting this photon has to, that photon has to pass interstellar medium, circumgalactic medium, and the intergalactic medium to reach us. And as this probability of passing through decreases as we go more distant from us, so we get to see almost very few galaxies, this kind of photons coming to us. The first discovery was made in 2020 when we observe redshift 1.42, this galaxy which already was imaged using Hubble Space Telescope. And this image taken by Astrosat UVIT confirmed like this galaxy is actually leaking. And this detection of leakage of ionizing photons is very important to understand the cosmic reionization process. So this is one of the greatest discovery by our own Astrosat UVIT telescope. We are also working on different other things, like, as I told you, observing at different wavelengths from extreme UV, UV2, infrared. So when you go from high energy to the infrared bands, you actually start tracing different things like stellar population, then you have older stars, and then you have emission from the dust. Now, when you combine all this emission for a same galaxy at different region, you get the full picture of a galaxy. I'll not go in more detail of other studies we're doing using observation of Indian facilities and international facilities. Just want to end my talk with these pictures, like as I started from the nearby galaxies where we can see much more finer details, like this is a galaxy image, the nearby to us, taken in by JWST, and this is the image where I was saying every tiny dot is a galaxy at different distance. So from here to here, we have actually covered physics of different scales, physics of different uh, nature. So we are still exploring a lot of new things every day with new observations. So I will say every galaxy has its own story, and we need to unfold it to understand the universe well. I thank all of you for your attention, and I'll end my talk here. If you have any question, please feel free to ask.
Thank you very much, Dr. Chayan, for this very elaborated and uh, very enlightening talk. Now I will request the members present to raise their question. We have very versatile group, Dr. Chayan. We have a school student from Ribadi, and we have our senior founder members, Dr. Arvind Kulkarni, Madam Deka, Madam Vandana Luthra, and all other Professor Bharat with us in this talk. So I'll request,
Yeah,
please,
thank you.
uh, put your question if you have regarding this talk.
So, like, it's not exactly a question, but I wanted to ask from where we collect data of those spectral lines, because I usually use SDSS, Slow and Digital Sky Survey.
Okay, so are you kind of indicating to, sorry, maybe I sort spectra over here.
Yes, these.
Okay, so like you used the SDSA, so this spectra was taken using uh, Keck telescope, you know, right? So this is the Mossfire survey, part of the Keck telescope, and optical spectra taken using. Sorry, this is the LRS optical spectra, and there is the same telescope used for observing the infrared spectra also. So SDSS is an optical telescope, observes in the optical bands. So similarly, Keck has both optical and infrared. So this observed spectra, Keck observed spectra.
Yes, sir. Thank you.
Dr. Chayan, how Rubin camera will help us to view a new kind of images of these galaxies, apart from what you have shown us? How Rubin camera will help us?
Okay, so Rubin basically has so Rubin is designed to scan the sky uh, to identify the transients mostly, which changes or appear suddenly. But apart from that, Rubin also has a very good sensitivity.
Okay.
So initially, when Rubin started observing, so mostly you will be benefited to detect the transients or any other astrophysical source which changes their intensity. But over the time, when Rubin scans and gathers more and more light, visit the same part of the sky, you can increase the signal to noise ratio. At some point, you also start getting beautiful image or very deep high signal to noise image of these galaxies which I was showing you. Yeah. So you may have to wait some more time to get the best out of Rubin for these distant galaxies.
Very interesting and enriching talk. I just want to know, in this case, the data is a huge set of data. So AI ML models are being applied in this. So could you enlighten us on that?
Yes. So let me go to a picture. Okay, sorry. Yeah. So the best contribution, I would say, by the AI. So there are many fields where AI/ML has been used to study the huge set of data, as you said. Now, the first thing I think people started exploring using AI, machine learning, how you can identify or characterize the morphology of these galaxies. So whether the galaxy is disky, having some spiral arms, or it's kind of a spheroid or structureless. So a lot of studies have actually used machine learning to automatically characterize galaxies when you have these millions or thousands of galaxies. It is impossible for a human being to do one by one. So yes, AI ML has helped a lot in that. Also, recently there are many other fields where we use machine learning uh, to better understand the huge set of data these telescopes are actually giving every night. For example, like this redshift estimation, as I said, like we take different approaches, right? From the spectral lines or from measurement. So now people are also using AI ML to see whether you have some galaxy where there is overlap between two nearby galaxies, and you, because of the blending, you see some uh, uh, so the percentage of this which can be blended, and you have to produce some method where this can be automatically identified, and uh, for example, this galaxy is a single, and this galaxy might be an overlap of two. So AI, some people are working on that to automatically identify that, and many other things like that. Yeah, yeah. So it's a must thing for us to tackle this huge set of data.
Yeah, thank you so much. And also, what information are we getting about the dark matter and dark energy using these data analysis which we are doing of different galaxies?
Uh, So the dark matter and dark energy is something which I have not studied and talked about in this. But if you have heard about this survey by another telescope called DESI, so what they also do, they survey the entire sky, like collect data from lot of galaxies and other sources like supernovae. And when you collect uh, this kind of data from entire, so this is a small part of the sky, but when you have measurements across the sky at different places, we can constrain how the dark matter and dark energy actually evolved from earlier to the recent time. So uh, I am not an expert to comment on that, but statistical measurement of large sky surveys using DESI telescope has given a lot of insights, new insights about this dark energy very recently. Yeah,
Thank you so much. Very interesting and informative talk. Thank you very much.
thanks. Yeah.
Hello.
Yes, yes.
Hi.
Uh, yes. Can you enlighten some research paper to start a journey in astrophysics, like in your field, like which papers are for beginners to advance to study?
Uh, so you mean like for galaxy or anything in the astrophysics? Like in general, you want to start with
In
astrophysics?
general, for starters, for general, and then in particularly in galaxies.
Okay, so if you want to start something, I would rather suggest books which are better to start with, or some review articles. Maybe later I can forward some to Professor Hemant, and he can definitely circulate. And maybe I can also suggest some papers, but I would suggest to start with either review article or books, which I can recommend
Thank you, sir.
later.
Particular writers, if you have
Sorry?
any particular author you can suggest.
Yeah, so that's what I said. Like I can send the information after this talk.
Okay.
So there's
Okay. Okay.
one book by Halle Bratt, by Halle Bratt. It's the astrophysical process. That's a good book to start with. But yeah, I can send the information later. Yeah.
Professor Arvind Kulkarni, sir. Hello, Kulkarni, sir. Please unmute.
Yeah, it was a very informative. I heard the later 70% of it. The first 30% I missed for some reason. It was a very informative talk, very rich in information and processes, and I'm sure those who are attended have definitely benefited in some way or the other. The attendance was not bad, about 18 to 20 roughly. I expected to be a little more, but it doesn't matter because now these are exam times and festival times, so people will be missing. And I'm sure down the time it will be. This was very informative talk. Thank you, Mr. Chayan. Okay, wonderful. Thank you.
Thank you, sir. Thank you very much.
Thank you.
Takshay, do you have some question? Takshay, youngest member of our group.
Yes.
No, sir, I have understand clearly and some, sir,
Okay.
all.
Have you enjoyed the talk? Images?
Yes, sir.
Okay.
Yes, sir.
Okay, right.
Great, Akshay.
Any other question? Madam Deka?
was it was really a very wonderful talk, and he has explained to us in such a nice manner, very easy to understand. And it was really informative and very nice. I hope he will give us more lectures in future. Thank you so much.
Thank you so much. Yeah, definitely. I love to.
Thank you, madam. Thank you.
Thank you so much.
So I think there is no more question in chat box. Uh, so thank you very much, Dr. Chayan, for giving this very illustrative and a very informative talk. And you accepted our request uh, in spite of your very busy schedule, and you spared time for us. On behalf of NASNI, I thank you for sparing time. And also, I extend thanks on behalf of NASNI to all the members present, especially Professor Arvind Kulkarni sir. He is always with us and guiding us at different stages how to take the NASNI forward. Madam Deka, Madam Vandana Luthra, and all other senior members and students from various institutions. They are with us, and I am sure this exposure of the entire talk will be very beneficial in the coming times for the students, especially. And I hope that Takshay will take this information to his entire life, because he is attending all the lectures of NASNI, and he is very regular member of our audience. Thank you, Akshay, to be with us all the time. And once again,
Thank you, sir. Thank you, sir.
thanks to your parents also, who are guiding you to sit with us and listen about astronomy. So once again, I thank you all for attending this talk. This was 19th talk, and next time on 20th talk, I wish all of you will attend the next talk also. So wish you all very happy festival coming in the coming days. Happy Diwali and all other festivals. Thank you so much, and thank you, Chayan sir.
Yes, thanks,
Thank you, sir.
thanks,
Thank
Dr.
you,
Hemal.
sir.
Thanks everyone for joining. And yeah, I loved it a lot. And see you next time. Yeah.
Thank you so much.
Thank
Thank you.
you, sir.
Now I sign off the session. Thank you.
Bye.
Bye.
Thank you,
Sir,
sir.
thank you, sir.
Bye, sir.